Okay. On the other side, you can see the experiment, which in the tube you can see the hydrated copper 2 sulfate, which is contained of water, and it's blue color. So if you apply a heat, then the water can be released, can be left the chemical, and can be collected here in this part. So if you change the condition, I mean, if you add water or if you add water vapor, so then it can be changed again to the light, to the blue color of the chemical in the uh, previous condition. All right, let's have a look at a dynamic equilibrium. What is dynamic equilibrium? You can see one example in your book in that page, but here I put a simple definition. At the dynamic equilibrium, the reaction rate of the forward reaction is equal to the reaction rate of the backward reaction. That means the number of particles are same in a reaction, but sometimes the forward reaction can go through more, or backward reaction can back more, but they have a same particle. But what is the condition for the dynamic equilibrium? That means both sides are equal. So during the reaction, it takes time to the reactants convert to the products, and products convert to the reactants during the reverse reaction. But the time which both sides are equal is called dynamic equilibrium. That means um, yeah, that means the reaction is stable and not reacting. The reaction is not moving anymore. One example to produce ammonia, which is a famous for producing ammonia, is an industrial reaction. Is called Haber process. So Haber process is applied to making ammonia. This is a kind of reversible reaction, and it's widely studied in institute, university. As I mentioned before, if you see this double arrow, forward and backward, meaning that the reaction is reversible reaction. First of all, in the first part, there is a one forward reaction when nitrogen gas react with three molecules of uh, hydrogen gas and then produce two ammonia gas. Ammonia gas is not that much stable if situation is same, if the condition, physical condition is same. So that is able, ammonia is able to break down and then produce nitrogen gas and hydrogen gas. So here on the other side you can see the reverse reaction. This can be happen at the same condition and same time. So this reaction move forward, move backward until this reaction proceed a dynamic equilibrium. So that means they're stable. But how we can separate the ammonia if the purpose is uh, to produce ammonia? If we just wait for the reaction will not stop at the production. It will give you a mixture of ammonia, nitrogen gas, and hydrogen. So this is very important to know how to separate the ammonia. As a summary, a reversible reaction is an equilibrium when the rates of the forward and reverse reaction are equal. The amount they produce products can be same the amount they produce reactants, forward and backward. At equilibrium, the concentration of reactants and products do not change. So they are still same. The equilibrium concentrations for particle reaction depends on the condition used, like temperature and pressure. So as as you remember, I repeated many times that physical condition. I said at the same time and same condition. Condition or physical condition can be mainly divided two parts, temperature and pressure. If we play with these two factors, we can change the behavior of chemical reaction. So for a reversible reaction, a catalyst does not alter the equilibrium concentration of reaction. So catalysts, as we learned before in previous session, catalysts only help the reaction to be faster, help to make it quicker. But catalyst does not change chemically, does not uh, cannot be used, is not used during the chemicals. So amount or concentration of the catalyst is usually is a solid structure, solid phase, but it doesn't alter the equilibrium concentration. All right. So as I said, a wide range of studies have been done for this reaction, Haber reaction, to find the best physical condition in terms of temperature and pressure. So here you can see a plot which shows you three different temperature. So they did an experiment to produce ammonia at 550 Celsius, 450 Celsius, and 350 Celsius, and in a range of pressure from 0 to 400 atmosphere. So between these three, and this side also, this side shows you a yield of ammonia at equilibrium percentage. Okay, so this is the amount of products, yield of product. Between these three temperature, which one has the highest amount of ammonia? Which ammonia produced in which temperature? So it's clear at 350. So it doesn't mean if we increase the temperature, so we will get more ammonia. No. Lower temperature shows a better temperature. How about the pressure between the range pressure between 0 to 400? So 400 can be the best choice. So finally we can conclude that in high pressure, the highest pressure and lowest temperature, we can produce more ammonia, because we know that Haber reaction is reversed. So once they produce ammonia, ammonia can be broken down and then reversed back to the reactant. So there is one principle which is called Le Chatelier's principle. It states that when a change is made to the condition of a system in dynamic equilibrium, the system moves so as to oppose that change. So if we change the condition, actually simply if we fight with the condition, then we can get the product. So As I said, we can change pressure and temperature. Changing pressure. Here we can see low pressure, high temperature. We have in low pressure, we have lots of reactants, but the product is very low. If we have high pressure, that means in a container we have high pressure of gas. If we have high pressure of gas for hydrogen, then we can get more ammonia. About the changing of the temperature, another factor. So a forward reaction is exothermic, that means heat given out, and a reverse reaction, that means breaking down ammonia, is endothermic reaction, that means heat taken in. They need temperature. So you can see if we increase the temperature, that is not good, because if we increase the temperature, ammonia can be broken down easily. That's why we need to reduce the temperature. Once ammonia produced, then the condition is not suitable to reverse the ammonia back to the hydrogen and nitrogen. That's why we need to reduce the temperature, but not in all the time. Always it says optimum temperature. That means not means if we decrease as much as possible the temperature, so that means good. No, optimal temperature. So let's have a summary about Haber process. Nitrogen gas and hydrogen gas are mixed in ratio of 3 to 1, because based on the chemical formula of the ammonia, we have 1 nitrogen and 3 hydrogen connected to nitrogen. So that means 3 to 1. So we need to follow the ratio in reactant. An optimum temperature of 450 Celsius is chosen, can be a good one. A pressure of 200 atmosphere is applied. A catalyst of finely divided iron is used. Okay, the ammonia is condensed out, the reaction mixture, and remaining nitrogen and hydrogen recycled. Once the ammonia has been produced, then the ammonia can be collected from any experimental container or experimental tube. So they can be collected. Once they collect, they will not have chance to reverse to the reactants, hydrogen and nitrogen gases. Condition affecting a chemical equilibrium. So there are some general idea for our today's discussion, which is summarized in this table. This table is important, please, because it's a summary of whole this part. Catalysts, as I said, catalysts don't affect on the rate of dynamic equilibrium, or doesn't affect on the reversible reaction, but just they affect on make the reaction to be faster. So temperature we learned in the example of Haber reaction. So reducing temperature can be appropriate strategy. And concentration, so concentration has not changed during the reverse reaction. Concentrations are same, And pressure in the example, so said temperature pressure can be considered to be higher pressure, but it depends on the type of reaction. So that's all for today. Please look at this question, memorize your lesson, and then submit your answer. Thank you so much. Stay safe at home and take care.